Okay, so good afternoon to everybody. Welcome to this ninth seminar within the JUS Colloquia. Today we have the pleasure to have a speaker, Dr. Paolo Scarabaggio. Please, Paolo, could you please share the screen and show yourself, please? Dear Paolo, good afternoon. Let's see with the slide. That's perfect. Okay, so before starting with the seminar, I would like to spend a few words about Paolo. So Paolo received the bachelor degree in mechanical engineering, master's degree in management engineering, and PhD recently from the Politecnico of Bari. He's currently a researcher at the Decision and Control Laboratory of Politecnico of Bari. In 2019, he was a visiting student at the Delft Center for Systems and Control, UT Delft, and his research interests include modeling, optimization, game theory, and control of complex multi-agent systems with application in energy distributed systems and social networks. So Paolo is recipient of the 2022 IEEE Control Systems Society Italy Best Young Author Journal Paper Award. And in fact, we are very happy because this is the first seminar within the JUS Colloquia that is also sponsored by this organization, again, the IEEE CSS Italy. So thanks again, Paolo, for being with us. You can start.
Thanks, Professor, for your really nice introduction, and I'm really honored to be here, actually. And so I'm going to present a really short seminar about seeking Nash equilibria under nonconvex coupling constraints. But first of all, I want to thank Raffaele Carli, Sergio Grammatico, and Maria Grazia Dottori for their really deep contribution to this research work. I will start just with a really short introduction on why game theory is so important. And I will use actually a quite strange example that comes from the COVID-19 pandemic, where, for instance, at the European level, we had that several independent decision makers, for instance, the European Commission, the government, the municipality, they had several different reactions to the pandemic, but this action, they were all uncoordinated. So actually, the action of one of these players, let's call them in this way, impacted all the other decision makers. So this is the perfect case on why game theory can be useful to model such a situation. But let's go more on a formal way. So let's formalize what is actually a game, and we can define it by a set of players we actually play in the game, and we can define a set of this player or decision maker. And each of these players have a decision variable that you can select from. It's called local feasible set. So he has its own constraints. And let me also define two more vectors. X, which is a vector which collects all the strategies of all the player, just stack together all these strategies, and X minus I, that collects all the strategies of the player different from the player I. Okay, so actually, what makes a game different from a classical optimization problem is that in the cost function that here we call payoff function, that actually represent the objective of the single player, we have not only the decision variables of the player I, but we have also all the decision variables of the other player. So actually, it's actually welfare, its outcome is dependent also on the other player. We have several ways how to find a solution to a game. So actually, find a solution for all the player. One of the most famous is the so-called Nash equilibrium, but it's not, of course, the only one. And the solution of this player is basically an interconnection of an interdependent decision problem that you can find here, where each player aims to minimize its cost function. And the nice things about the Nash equilibrium that when we reach it, no player wants to change his strategies because there are no other strategies that he can select that can increase its welfare if all the other players don't change the strategy. But from a control theoretic perspective, the objective is to find a mechanism, so basically an algorithm or a discrete-time system to update the strategies of this player. So actually we can also define it as a state of this player to a Nash equilibrium. A further improvement of this model is the so-called generalized Nash equilibrium, where we don't have only the interconnection between the cost function, but also within a so-called coupling feasible set. So actually we have that each player cannot select a strategy from only its feasible set, but the coupling feasible set is actually the interconnection of the single player feasible set. That is a really harder problem with respect to the Nash equilibrium problem. And in fact, the question that can arise from defining a generalized Nash equilibrium is to find it and also to prove its existence. When we talk about generalized Nash equilibrium, we need some technical assumptions in order to ensure the existence of this equilibrium, and these are, for instance, the continuity or the compactness of the sets that are involved in the game. But these two assumptions can be actually relaxed with other assumptions. But one of the most important assumptions that we need, and we cannot actually relax, is the convexity. And actually, this seminar is focused on relaxing this further assumption. Okay, this is really important for ensuring the existence or even the convergence of solution algorithm, because most of the time the proof that demonstrate the existence of an equilibrium are based on the fixed point theorems that actually require the convexity. In fact, in the related literature, one class of Nash equilibrium, of generalized Nash equilibrium problem, is really common, and this is so-called jointly convex Nash equilibrium problem, where we have the convexity assumption, and in this case we can ensure the existence and the convergence to this equilibrium. I will take now a small break on game theory to talk about the variational inequality problem. Why I need to talk about this? Because some class of games are solved through this other problem, and then we will see why. But let me introduce this problem. So basically, we introduce the variational inequality problem, and to define this problem, we need a set. So a set that is actually the set where we can select the variable x, and a map that we call it F here. So the variational inequality problem is the problem of finding a vector in this set that respects this relation. Okay. The variational inequality problem is defined only on closed and convex set and on continuous mapping. To improve this problem, we can define the quasi-variational inequality, where actually we make not only the map, but also the set dependent on the vector x. And in fact, the set, it becomes a point-to-set mapping. We need the variational inequality problem because we can actually solve some class of generalized Nash equilibrium by solving the associated quasi-variational inequality problem. And in fact, we have, let me introduce two more assumptions, that is the monotone and the strongly monotone assumptions on the map F. And these are properties of the mapping. And actually, we have that when the mapping F is monotone, the solution set of the variational inequality is closed and convex. If we strengthen the assumption on monotonicity, so we make it strongly monotone, and here you can see what means to be for a map to be strongly monotone, we have that the solution of the variational inequality admits a single solution. So let's see how we can actually solve a game through a variational inequality problem. Well, basically, we define the mapping F by stacking together all the subdifferential or the subgradients of the different player. So we just take if the cost function F is differentiable, we just stack together all the differential, okay? And we actually define the set in the variational inequality as the intersection of the local visible set of the different player. So in this case, if we define the variational inequality in this way, we have that the solution of the variational inequality are exactly the same solution of the Nash equilibrium problem. Okay, so solving the Nash equilibrium problem is equivalent of solving the variational inequality defined in this way. Similarly, we have that if we define a quasi-variational inequality problem by changing the feasible set with the coupling feasible set, because in generalized Nash equilibrium we have that the coupling feasible set is coupled within the different player. We have a similar relation, so that we have that all the solution of the generalized Nash equilibrium are solution of the quasi-variational inequality problem. In case of jointly convex generalized Nash equilibrium problem, we can actually use the variational inequality. So this is easier actually to solve, but we have a drawbacks, because then we have that all the solution of the variational inequality are solution of the generalized Nash equilibrium problem, but the opposite is not true. Why is not true? Let's characterize the solution and let's see why. If we take, for instance, the optimality condition of one single player, and then we take also the same condition for the corresponding variational inequality problem. Here I'm assuming all the assumptions in order to use the KKT condition. So I don't know if you are aware, but I just want to point out that that by showing the two optimality condition, the case of the game and the case of the variational inequality problem, we can see some relation, and actually we have that all the solutions that we find with variational inequality problem, so all the solutions that we find with this problem are the one that actually keep all the Lagrangian multiplier for the coupling constraints. So the nice things of keeping the Lagrangian multiplier equal for all the different players is that the equilibrium is actually fair, because I'm actually sharing fairly the coupling constraint to all the players. So we can actually also define a kind of convexity for the mapping F, before I call monotonicity. And we have that if we define the cost function of the different player as convex, we have that the mapping F is monotone. And we can actually, if I go back, we can actually say that if the mapping F is monotone, the solution set is closed and convex. So actually the solution set of the generalized Nash equilibrium with equal Lagrangian multiplier is closed and convex. If, for instance, F is strongly convex, then F is also strongly monotone. And in this case, an equilibrium, so a Nash equilibrium, exists and is unique for the characteristic that I just showed before. So this is actually what we have in the literature. So we have that we can use the variation inequality to solve some generalized Nash equilibrium problems. And in this case, we needed the convexity assumption, and in particular, the convexity assumption on the coupling visible set. But this is not the case in several different applications. For instance, here there are some cases arising from power system engineering, where we have, for instance, to solve the so-called optimal power flow problem, where the power flow equations in a power grid, are highly non-convex. And in this case, if we imagine a group of players who participate in an energy market, then they have to share these constraints, which are non-convex. If I move then to another example, we have that we can also define some games in radio system where we have some power allocation problem. And also in this case, we have some constraints in the frequency in communication channels. And most of the time, in some problem, these coupling constraints are also non-convex. Then I move to another example, which is actually quite new. This is so-called eigengame, which is basically a solution of the principal component analysis as a Nash equilibrium. So actually take a problem that is really computationally expensive. So
I cannot hear Paolo.
Of the problem. And in this case,
Paolo, can you repeat, please, because it was not possible to hear you in the last seconds of this slide.
Yeah. Okay. No. Okay. In this example, we can actually solve the principal component analysis. That is basically the problem of finding the eigenvector of a really big data set. It can be also small, but it's really used when the data set is really big. And we actually give to each player the goal of finding one eigenvector of the original problem. And we can actually parallelize this problem and make it easier to actually solve. And in this case, we have that there should be a coupling constraint between all these, between all the eigenvectors that the solution must select, and this constraint is highly non-convex. Okay, so let's go ahead And let's try to actually relax this assumption on the convexity of the set. And so let me just introduce a couple of assumptions that are, the first one is a really standard assumption on game theory. So we assume that the cost function are convex and continuously differentiable. And actually, I'm assuming also the standard assumption on the coupling feasible set. The only things that I just relax here is that the set can be non-convex. So as I said before, it's quite hard to find a classical Nash equilibrium in case of non-convex set. Actually, it's almost impossible to prove it. So we actually search for weaker equilibrium conditions. And we actually came up with a new concept that we call Clark's local generalized Nash equilibrium. Why we call it Clark? Because we actually use the Clark theory on the tangent cone to define this equilibrium. So we actually we take the classical generalized Nash equilibrium and we change the coupling feasible set that can be non-convex with the Clark's tangent cone in that specific point. Okay, so the nice things about this problem is that when the set is convex, this problem is equivalent to the generalized Nash equilibrium. And another nice thing is that this this new set, time varying, sorry, not time varying, is actually mapping to point set, is also is an approximation of the original set. This set is always convex for how we define it, since the Clark's tangent cone is always convex. And for this characteristic, it's really important because we actually can prove several properties thanks to the convexity of the tangent cone. For the one who never heard about Clark's tangent cone, these are basically the collection of all the Clark's tangent vectors of a generic set to a specific point of the set. For instance, in this case, we have this point x, and in this case, the tangent, the Clark's tangent cone is this one. In case the set is convex, the Clark's tangent cone is equivalent to the set. So after defining this new condition, we can actually write the optimality condition, the classical optimality condition of this new equilibrium using using, for instance, the standard optimality condition or also the KKT condition. And we have that actually this point satisfies the KKT condition, so it's an optimal point from an optimization point of view. And furthermore, we can actually modify a standard quasi-variational inequality problem that I showed before that can be used to solve the generalized Nash equilibrium problem to solve the Clark's local generalized Nash equilibrium problem. So what I'm doing, I'm just taking a quasi-variational inequality and I'm changing the original coupling set with the tangent cone, the Clark's tangent cone. And we define a new subset of equilibrium points that we call it variational, because they satisfy, let's say, some nice characteristic as the case of as the convex case. In fact, similar to the relation between net and variational inequality problem, not all the solution of the Clark's local generalized Nash equilibrium are solution of the quasi-variational inequality problem, but we have the opposite relation. So here I just included a recap on of the relation that we actually saw on the previous slide. And I recall that by solving the generalized Nash equilibrium problem is equivalent on solving the quasi-variation inequality problem, where we have the coupling feasible set here. If we want to make it simple, we actually can use the variation inequality problem, but we need to assume that the feasible set are convex. In our case, where the feasible set are non-convex, we need to use the quasi-variation inequality, but we still keep the same relation, so that all the solution of this quasi-variation inequality are solution of the Clark's local generalized equilibrium problem. This can be proven because this, as I said before, this new set, so the tangent cone in a specific point is convex, and so we can actually prove that only the variational solution are passed from this problem to the other problem. And as for the case of jointly convex games, we have that one variational solution of the Clark's local generalized equilibrium problem is a locally fair equilibrium point, because in the tangent cone actually there are not other equilibrium that have the same Lagrangian multiplier as the case in the convex case. So let me show a couple of examples just to show better this new concept. And let's start with a really easy example where we have two different players. They have a really standard and easy cost function or payoff function that is actually strictly convex, and we have a coupling feasible set. Okay, so actually we have that only the area outside of this unitary circle is a feasible point for this game. If we solve and characterize this game through the KKT condition, we have that actually the Lagrangian multiplier are 1. So this is a really particular case where all the points of the circle are variational problem of the Clark's generalized Nash equilibrium. But the really nice thing is that each of these points we can say that is unique in its tangent cone. By just changing a little bit this example, so just moving a little bit the circle, we have that optimality condition they change, and in this case we have only two different equilibrium points, so two different variational solutions that are the one indicated in the slide. The nice things about this concept is that actually we have different multipliers for this point. So we can actually see a difference between all the different equilibrium that we found. But also in this case, they are unique in their tangent cone. So after defining the existence of after defining this new problem, let's see if we can actually prove the existence and uniqueness of this point. But before doing so, I need to introduce some operators. The first one I will introduce the projection operator, well-known projection operator, and the distance operator between a point and a set. And then I will recall what is actually a Lipschitz continuous function. It's a function that has that respect this relation, and we say that actually a function that is Lipschitz continuous is Lipschitz continuous with a specific constant L in this case that is actually greater than 0. When actually this constant is equal to 1, we say that f is non-expansive. When is less than 1, we say that is a contraction, and we call it a contraction factor. The nice things of working on the convex set is that the projection operator is a contraction when we define the projection on the convex set. And by having the projection is a contraction, we can actually show a lot of different nice characteristics, but one of the most important is we can prove the existence and the convergence of, for instance, projected gradient demonstration approach, as you can find here. So we actually need only to find the fixed points of the projection operator, or projected gradient operator, and we find the solution of the problem. But as I said before, we are working on non-convex set, and in this case, the projection operator is a non-expansive operator. What does it mean? It means that the L, so the constant, is greater than 1. So all the proof, the classical proof of existence are not cannot be used. So the question is now, can we ensure that the projection operator is a contraction also when the set is non-convex? Or the other question is, can we also use the projection operator by assuming that it is an expansive operator, but with a certain degree? So can we still prove the existence of an equilibrium when this L is greater than 1, but is bounded in some way? Well, actually, yes, we can do it, but we need to include a technical assumption that is the proximal smoothness properties of the set. And here I want to show these properties on this example. And basically, you can see here the original set in black. And you see here another set that contains the original set that is called an air enlargement of the original set. So actually we take one coefficient air greater than 0, and we create another set that contains the original one. When we have that distance function between a specific point in this enlargement and the original set is differentiable, then we have that is continuously differentiable. We have that the set is proximally smooth. The nice things of having these properties is that actually the projection is a singleton, that the projection always exists for any point contained in this enlargement. And we have also that the projection becomes p-Lipschitz continuous with an air greater than 1, but bounded by a specific constant. And by recalling all these properties, we have that the projection operator from a point in this enlargement to the original set is well defined and norm-to-norm continuous. Informally speaking, we have that the local non-convexities of a set are counterbalanced with the smoothness of constraints. So we enforce the smoothness of constraints to counterbalance the non-convexity of the set. For instance, here I'm going to show you some example of proximally smooth and non-proximally smooth set. In this case, I have one circle, okay? and is of course is a convex set. And in this case, this set we can say that it's approximately smooth with constant, with infinite constant. So the R is equal, the R, characteristic R, is actually for the convex set is infinite. Here you see another example. That is the one that I used in the previous two examples. This new equilibrium concept is when we have actually the area outside one ball, and then we have that this is R proximally smooth. So we have the radius of this ball is actually the constant, the proximality constant. But we have that this property is actually is not preserved when we also include two different sets. For instance, in this case, I am merging two different convex sets that are actually two square. I put them together, and actually the set that I obtained merging these two actually convex set becomes non-proximally smooth, since I have let's say an angle here, but actually also, for instance, merging two different convex set that I said here that are proximally smooth. In this case, they are not proximally smooth. But there are actually some conditions, so sufficient condition to guarantee the proxy regularity of this set. So actually we can merge two different sets, convex or non-convex, or proximally smooth and convex, and ensure that the union is actually proximally smooth. We need only to ensure that actually all the constraints that define the set are differentiable and Lipschitz continuous on the R enlargement of the set. And actually we need only to show that this condition is respected. This condition, in case of a single equality constraints, equality or inequality constraint, actually can be also not considered. So when we have a single coupling constraints, we need only the differentiability of the constraint. So this makes this approach really useful, as we need only to show that the coupling feasible set is made out of one single equality or inequality, and that this equality or inequality is differentiable. So having said that we need to include these assumptions when actually we want to prove the existence of this equilibrium, we can actually show that with the standard assumption that we used and considering that the set is non-convex, we can obtain actually sorry, I don't know why it's going. We can actually show this this proposition where we show that when the set is proximally smooth, then we have at least one variational Clark's local generalized Nash equilibrium. And also regarding, for instance, uniquenesses, we have that we can ensure the global, since we are talking about non-convex set, but we can show the local uniqueness, but that this local is restricted in the Clark's tangent cone. So let's move now, once we define this new equilibrium concept. We show that it exists under this new assumption, and that is actually unique. Let's show how we can define some algorithm to reach this equilibrium. And we actually show the convergence on two different assumptions. The first one is the assumption that the pseudo-gradient mapping, so actually the F, so the collection of all the cost function of all the gradient of the cost function are strongly monotone. And here I recall what is actually strong monotonicity. And in this case, we can use the classical projected approach. Of course, the step that we must use with the classical projected approach is actually smaller than the classical step. But still, if the set is proximally smooth, we have that an equilibrium exists, and we can converge to this equilibrium with this algorithm. How we prove that this algorithm can converge? In this case, it was quite easy, since we needed to only include the assumption on the proximality on the set, and we actually needed only to include this term p, that is the Lipschitz constant of the projection on the actually the projection of this nonconvex set. And in this case, the key idea of this approach is the counterbalance the expansiveness of the projection operator, because this is actually a constant greater than 1. So actually the projection is an expansive operator in this case, since we are talking about nonconvex set. The key point is to counterbalance this expansiveness property of the projection with the strong monotonicity of the pseudo-gradient mapping. So we use the strong monotonicity of F in order to counterbalance the actually expansiveness of projection. Let's move on and let's see if we can still prove the convergence in case of only monotone pseudo-gradient mappings. In this case, this is actually a weaker properties respect to the strongly monotonicity. And here I recall also what actually means for a function, for a mapping F to be monotone. And in this case, we had to actually modify a well-known approach in the literature. And we had to also prove again how this approach can converge to equilibrium. And also in this case, we find a gradient step for this algorithm that is lower than the classical approach, because of course we are considering nonconvex sets. The demonstration of this approach is really long, so I will not show it, but I just want to show how this approach works. So we start with a generic point x that is contained, that can be also not contained in the original feasible set, and then we actually compute a new point that is basically we move in the direction of the gradient of f, and we obtain a new point. Sorry, is this? We move here and we obtain a new point based on the gradient of f. Then we project this point to the original feasible set, and actually we take this point and we use it in the second step of the algorithm, where we start again from the original point, but we use not the gradient that we use in the first step. So the gradient computed in this point, but we use the gradient computed in the new point that we compute. This is included in the set, as you can see here. The second iteration then, once we define this new point, is projected not on the original set, but on the tangent cone computed at the point computed in the first step. Probably is a bit confusing, but the only things that I want to point out that is important is that we can do all these things. We can prove that this approach converges because we ensure actually that at each iteration, the y that we compute is included in the original feasible set. The x, so the first point that we use is contained in the not on the R enlargement, but on an half R enlargement of the set. So we have a set that is a little bit greater than the original set, but we ensure that the iteration are all contained in this new set. And we ensure that also when we move from this original set away to find a new point, we ensure that there are contained all on the R enlargement. Why we need to do so? Because if we go outside of this area, we have that the projection is not well defined, and all the nice properties of the projection operator cannot be used. So we actually also in this case we use the assumption of on the mapping F, the monotonicity assumption, to counterbalance the expansiveness of the projection operator. But in this case, we have to be careful that each iteration is contained in this enlargement of the original set. But this is not hard to have, since if we select the original starting point inside of the original set, then in employing this step, this gradient step, then we can ensure the convergence of this approach to an equilibrium. To show also some example of practical example of this approach, I'm recalling the first two examples that I showed before. So the one where we have a constraint, a circle constraint, standard circle constraint. Note in this case we have the
Let's wait for Paolo to come back to us.
Of the plot.
So Paolo, please, can you repeat? Sometimes we cannot hear you.
Yes, I think that I have some problem with the microphone. I will repeat. No, I just was just recalling the first example that I showed before. So where we have the feasible set as the area outside of this circle, and we have two different players that aim to minimize their goal. In this case, as I showed before, all the points of this circle are actually variational point. This is actually a really strange case, since it's really symmetrical. So actually, it's not like that. Most of the time, the equilibrium are 2 or 3. Depends, of course, on the application. And here you can see that the convergence of the first algorithm and of the second algorithm. If you see the second example, so the one where we have only 2 equilibrium points, In this case, it's interesting because we reach a different equilibrium depending on the initial condition. So, and you can see really nicely here in this phase plane plot, where if we select a specific initial condition for the strategy of the two player, we will reach a different point. And also in this case, I show you the convergence of the two different algorithms on this example. So as a conclusion, I show you a new approach to handle non-convex constraints, and I show you that actually we can show that this approach can respect some optimality condition, and also that we can prove actually the existence of this new kind of equilibrium. Also their uniqueness, local actually uniqueness, and also we show that we can converge to this equilibrium by assuming that the pseudo-gradient mapping F is strongly monotone or only monotone. We are actually still working on this research work, since we are actually proving the existence on more general settings, but in particular the convergence of distributed algorithm. In particular, we are almost close to show that we can actually reach this equilibrium also employing a distributed algorithm. But in this case, we need to, if you are curious, I can show you some more detail. We need only to assume that the coupling set is made of some functions that are actually separable. So we have to assume that the coupling constraints are separable within all the different players. So we need a further assumption to ensure the convergence in a distributed setting, and so on. If you are curious about this topic, you can find these two references, and you can also find it. This actually preprint online, but is available. And I really thank you for your attention. And if you have any questions.
Thank you, Paolo, for this very interesting talk. Are there some questions in the audience? Curiosities also. Yeah, Elena, please.
Thank you, Paolo, for your talk. It is very interesting. I had a question about decentralized convergence of decentralized strategies, but you already answered to this point. And I suppose that assumptions on the sets are very important because you have to choose independently the value of the strategy. Therefore, I think that the assumptions are really very important.
Yes.
Thank you so much.
Thank you.
Thank you, Elena. Are there some more questions, curiosities? So, Paolo, I mean, this is just a curiosity of mine. If you go, for example, to slide 34, this is just one. I mean, this is a very general question because honestly, I'm not expert in this research. So you are here, for example, giving a sequence, no? And then you are going to study convergence and etc. My very basic question is, how do you compute this kind of stuff? Okay, I mean, I guess you are not doing this by hand, right?
Is this a slide that you're talking about, right? So how?
Yeah, I mean, in general, you are talking about convergence of algorithms, no, to compute equilibrium, etc. So my basic question is, are there some tools that you can use to help you in doing this kind of computations or not?
No, this is actually depending on how is the how hard is the problem. But in case here I'm assuming that, for instance, the cost functions are differentiable, so this algorithm is really easy to implement. So I don't know why okay. So basically, you need only to compute the gradient of the different cost function of the player, and then you move toward the gradient. So as the classical optimization theory. And you can actually do it also in a semi-decentralized way. So you can make, you can ensure that each player is moving alone toward a new point, and then you may only do the projection in automatical way. I don't know if it's this the question or is a more technical question.
No. I mean, I was just wondering if there are some automatic tools that can help you in doing this kind of computation.
Well, actually, no. For classical game theory, there's something, but not for this, because it's really strange. To consider non-convex games it's really strange because it's really hard to actually find an equilibrium because all the mathematical theory that there is behind require convexity. Also,
yeah, I understand. Yeah, but I mean, non-convexity is a hard problem, not only in Nash equilibrium, but I mean, also a simple problem of computing invariant sets becomes very hard, no?
Yes.
With non-convex constraint. So it is, I mean, it is, and on the other hand, as you were showing, no, it is important to study this kind of problems because it arises in many practical, many practical situations, applications of interest. Yeah. So, I mean, I would have asked you to tell me which kind of application you can apply your kind of result, but I guess, I mean, this is a very hard, I mean, this is a theoretical result, and I guess perhaps there is some time before you are able to apply in practice to concrete case studies, this kind of theory, right?
Well, we applied actually to, you can find this some result on this paper.
Energy systems.
Where we actually we applied to a power system case. It's actually only on a simulation case, but it can be useful to consider, let's say, a market to find a market equilibria, considering also power flow constraints. So we actually included. It's not hard to do it. If you talk with some researcher on power system engineering, they are used to work with the optimal power flow problem that is non-convex. So they are used to work with non-convex problem. So they have like some trick to ensure that they select a good starting point. They call it the flat start point. So that if they select this point, they have the convergence to an equilibrium that they like. And so also we show that if you define the problem in a nice way and you start the strategies of all the player with a specific initial strategies, you will converge always to a specific point. And this is something that is actually done in power system engineering to consider actually the full non-convex cases, because especially like for large scale distribution system, you need to consider the full non-convex equation instead of using the classical convexified models, because they can be quite high, let's say.
Yeah, I mean, it is interesting, in fact, that you are already able to apply your very beautiful, I would say, theory to concrete applications. This is remarkable from my point of view. Congratulations. Are there some more comments from the audience? curiosities. My last question, I mean, this is this question because I'm a little bit biased because I'm working on, I don't know if you heard about this stuff about discrete abstractions, no? For verification and control and etc. Where basically you start from a nonlinear system and you discretize it to do some stuff in terms of verification and control. So my question is, if you have to handle a problem, a non-convex problem that is very hard, why not to discretize this problem and work with finite models? I mean, I'm not aware of the literature because I already told you that I don't know too much about game theory. I was wondering if there are some approaches in that direction.
Yeah, no, there are actually some approaches to discretize, to convexify the problem, but I like to show this example that I put, even if it's not so common to solve this. This actually is a new approach that is has been used by Google researcher, and in this case, for instance, you have the perfect example on that. If you define a game in this way, you cannot convexify it or you cannot discretize it. You have it in this way, non-convex. And this is also a problem that is in similar way is also researched a lot in machine learning theory, where they have a lot of non-convex functions, and they are also starting to studying some some game theoretical approach to solve these problems. So they use game theoretical approach to solve machine learning problems, and in this case, it's actually almost impossible to convexify or to discretize the equation. I mean, in the case of power system, or in this case, you can do it. For instance, in case of power system, they usually or discretize the problem, or they make a convexification for each step, let's say. But in this case, for instance, you really cannot. It's really possible. So, and that's why they are really starting now to work on this field.
Okay. So this gives much more motivation to the research direction you are studying indeed. Thank you very much. Okay, so if there are no more questions or comments, I would like to thank again Paolo for being with us today.
Thank you.
And say to you all good afternoon then. Okay? So thanks again. Goodbye.
Good afternoon.
Thank you. Bye-bye.
Bye.
Thank you very much.
Good afternoon.
Good afternoon.
Bye.
Bye.
So Paolo, I would like also to ask you to this part that we have not yet. Okay. Going to quit.